Well, hello everybody. My name's Professor Roger Moore from the University of Sheffield, and I'd just like to say it's a great honour to be invited to speak at this Furhat Conference on social robots in research. And what I'd like to talk about is voices, appropriate voices for social artifacts, why it matters and what to do about it. Now, we're all familiar with TV, film, and other forms of media where there are many artifacts, many devices, many characters who all have interesting voices. And here's just a few examples for you.
Pardon me, sir. Let me introduce myself.
Dobby has no master. Dobby is a free elf, and Dobby has come to save Harry Potter and his friends.
This is the voice of the Mysterons.
On your last trip, did you discover what the Earth people eat?
Excuse me, car collectors. I could save you money on your car insurance. Lead the way.
Stranger from the outside.
Aft laser turrets report an attacking battlestar.
Exterminate!
So what's immediately obvious there is there's a huge variety of different voices, and they all characterize the persona of the robot, alien, or cartoon character that's being portrayed. So these are designed. They're not just, they don't just happen. And here's one of the most famous designers, Ben Burt, a sound designer. He's behind many of the very well-known voices, particularly in films.
E.T. phone home. E.T. phone home.
And Ben's approach is to make these voices appropriate to the agent. As he said, I usually first think, if these objects, places, robots, or machines really existed, what would they sound like? Famously, he was behind the sounds of R2-D2. So how would they be powered? What would be the actual physics of how they work? Another one of his famous voices. Wally, which is so appropriate to the sort of rusty agent that Wally is. So this is what we're very used to in the media. And then we come to speech-enabled devices like Siri and Amazon Echo, Alexa and Google Home. And what do we find here? We find human-like voices. And indeed, there's huge pressure, an enormous amount of activity trying to come up with voices which are extremely human-like, such that researchers are very proud to develop speech synthesis, for example, which is indistinguishable from a human. So here's a recent example from Google. You're going to hear a couple of recordings. One is from a speech synthesizer and one is from a human being. And the challenge is for you is to identify which is which. There are two examples.
George Washington was the first president of the United States. George Washington was the first president of the United States. I'm too busy for romance. I'm too busy for romance.
So I've even forgotten which is which, but I think it's the second example, which is the, quotes, natural one produced by a human being. So that's fantastic, right? Amazing technology, but these devices are attempting to be humans. Now, is that a good idea? So what I want to talk about now is what it's like to talk to a machine, and particularly focus on usability and flexibility, because I want to characterize the way in which the technology has been developing over the last several decades. And so we've got these two dimensions here. So a human being is essentially in the top right-hand corner. A human being, in some sense, very flexible in language, and therefore you can do many different things by interacting conversationally with a human being. Whereas a lot of our systems, especially some of the early ones, which could only handle a few limited commands, is essentially down in the bottom left-hand corner. Not very flexible, a structured dialogue, and they're not very usable. You could do some things, but not very much. So there's, that's kind of understandable. What happened when Siri appeared is that it was shown what the power of combining speech recognition and some natural language processing or dialogue, and essentially take you a little bit further up the curve here, and providing more flexibility, and therefore one can do a lot more things. And so that's why Siri was very much a game changer, and something which Amazon Echo has very much picked up on and is in the same space. Now, this slide was given to me by Mike Phillips, who was behind SpeechWorks many years ago. And the question, therefore, is an obvious one, which is, so where are we on this trajectory from bottom left to top right? And this is Mike's suggestion of the trajectory. And so we see something rather weird here, which is that as flexibility increases, the usability suddenly seems to plummet. In other words, when we get a more complex system, which is voice-based, people suddenly don't seem to know what to do. And I've called this the habitability gap, which is a term borrowed from the HCI literature, where we have an interface between a machine and a person, and for some reason, it's not very habitable. Once we get a certain degree of flexibility, people then became very confused as to about just what is and isn't possible. Now, the issue here is related, I think, to language and a couple of other ideas that I'm going to put to you in a moment. Down at this left-hand corner, we're very much in sort of stimulus response space. So these were command-based systems, and the system just had to give an appropriate response. And this is very much like a tennis match analogy of language. This is not really language. This is just stimulus response behaviorist kind of view. Language is up here, of course, in the top right-hand corner, where we have human communication. And that's much more analogous to a coupled system between interlocutors, between people who are having a conversation. So here we've got a sort of three-legged race, and everything depends on careful coordination and coupling between the parties to achieve whatever it is, the rich sort of exchange that's possible using human language. And what we've got going on down here is we've got sort of mismatch between the capabilities. We've got a human being on one side and a machine on the other, and one or other of them has essentially fallen over. We've got mismatched capabilities, and we have a serious problem that one is falling behind, but still connected, and the whole thing begins, falls apart. So that's an analogy. Now, many of you, since this is a robotics meeting, many of you might have been looking at this curve and thinking, hold on, I've seen this curve before somewhere. And the answer is, of course, you have. This is the famous uncanny valley. The idea here was put forward by Mori in 1970, long time ago, which suggested that as we develop robots to look more and more human-like, as they appear more and more human-like, we get to a point where they suddenly become rather weird, and people react no longer. They don't react positively to them; they react quite negatively. And indeed, if the artifact is moving, then it's even worse. It's a sort of amplified, exaggerated effect. And so this has been very much studied over the last 50 years, with a lot of evidence supporting that this does actually occur. but not a lot of not too many explanations, and particularly no explanations which are quantitative, building models of this rather than just saying, well, it's because of this effect. I mean, for example, some of the things that people have proposed is that it's to do with feelings of mortality and death, for example. Anyway, I did some modeling of this myself mathematically a few years back, and basically used a Bayesian approach and showed that I could model these curves, and in particular the negative effect, by concentrating on conflicting perceptual cues. So the hypothesis here is that when you have a difference in one dimension or another, so if some aspect of the artifact doesn't look right, then this is the conditions under which the uncanny valley can arise. So there's lots of evidence which support this, and there's a particular paper here which I'm quite keen on, because it shows that, for example, if you have a particular face with a particular voice, if you have a human face and a robotic voice, or a robotic face and a human voice, that creates the conditions for the uncanny valley, exactly as Mitchell et al. Found. So what we need is, we want to avoid the uncanny, so we want a canny approach. We need to come up with a scheme which will allow us to avoid this. And what the model predicts is that we need to align affordances, which means that what a robot looks like, what it sounds like, what it can do, and what it appears to know, all has to line up. It can't have one of these aspects at a completely different level from some of the other aspects. And I'm just going to just present to you, one of my friends here, Bruce Ballantyne, has this lovely book called "It's Better to Be a Good Machine Than a Bad Person," which really captures the whole idea here, which is, when for creating artifacts for people to interact with by voice, why are we trying to create synthetic people? We should be creating good machines, not bad people. So there are ways of doing this. And I've got some evidence of this using a voice changer, where setting up a scenario where people are trying to interact with a service, and either they interact with a real person, or the real person whose voice has been changed to sound robotic. And in a nutshell, if the user hears a robotic voice, they are much better behaved. They know what they're able to do. They get right to the point. The length of the calls is significantly reduced, and interestingly, they're more polite, which is a kind of interesting outcome. So we can design voices. We should be interested in a technology for designing voices, and there are a whole bunch of techniques that we can use here. And this is a study that one of my students did a while ago, which showed how different effects lead to different perceptions. And, we studied some of the voices in the media, and were able to determine, for example, the difference between good and evil voices based on the various changes that people had made. So what we're interested in here is the arriving at an appropriate voice for an artifact. And if we're going to do that, we need to be able to assess the appropriateness. And I would suggest that one way of doing that is using the ventriloquist effect, which is to set up a scenario where the voice and the artifact are separated. And if the voice is appropriate, then the separation can be quite large. If the voice is not appropriate, then the separation has to be very narrow for the person to perceive the voice coming from the artifact. We've done some initial studies in this, and it appears to work. But the bottom line is that the Furhat platform is ideal for exploring these issues, and that's exactly what I plan to do. So in summary, the majority of fictional robots and aliens and cartoon voices are actually manipulated to fit the narrative context. They're designed and they're correlated with a persona in ways that we really don't think about in robotics, and we should be. So what we need is guidelines and tools which allow us to do this sort of thing, and we need to align the visual, behavioral, and cognitive affordances with the voice against a target persona. And Furhat provides a great platform for doing exactly that.
That's all, folks.
And so if you want to find out some more, there's a chapter in a book here, From Talking and Listening Robots to Intelligent Communicative Machines, and you can always check out my website. And that's it. Thank you very much.